As you can see here, we're going to talk about alternating series and particularly how we can determine whether an alternating series converges. It's called the alternating series test. But first we need to understand what an alternating series is, and it's simply a series whose sum has alternating signs, plus and minus. So as an example, -1 plus 1/2, minus 1/4, plus 1/8, minus 1/16. Notice we started with a negative sign and we're alternating signs in between. And generally in the summation notation, we see that developed with a -1 to a power on it. And so when that power is, and that power is going to change from odd to even, odd to even, odd to even, or even to odd. But this is what causes the alternating sign pattern to happen. Now here in this case we had our first sign was negative and then it went positive and so on. So it started with negative. We could have had the series where it started with positive that might look like this, but more frequently when we're starting with a positive, then we make our exponent on -1 n plus 1, okay? Because when n is 1, this will be a power of 2, which even powers of -1 are positive 1. So sometimes we can start at 0, but more likely we'll start at 1 and we'll have -1 to the n plus 1 power, and it will look like this. Now let's be clear. Just because we have different signs doesn't mean that we have an alternating series. So here's an example. The pattern of the signs is plus plus, minus minus, plus plus, minus minus, plus plus. That's not an alternating series. Certainly the sign pattern alternates, but the signs don't alternate from one term to the next over and over and over. So let's be clear on that. Well, there's a test that's pretty easy to apply when we have an alternating series to determine whether the series converges. It doesn't tell us whether the series diverges, but it can tell us if the series converges. And here is that alternating series test. I'll read it to you here, of course. Given an alternating series, so it's going to be one of these two forms, but we're given an alternating series. The series converges provided the following two conditions. Oh, by the way, up here, assume that the a sub n's. Now, this is a little different than what we've dealt with in the past. Usually we talk about the summation of a sub n's from n equal 1 to infinity. Well, in this case, the a sub n is not the whole term because the term includes either a positive or a negative sign that goes with it. But what we're dealing with right now is, okay, taking that positive or negative sign out of the issue when we talk about a sub n, that all these a sub n's have to, in fact, be positive or 0. I mean, they have to be greater than or equal to 0. Although I didn't say 0 there, but that usually doesn't happen. And the reason that condition is necessary is because if we didn't require a sub n to be positive here, this -1 changing -1 to a power, we might not end up having an alternating series because we might have some negatives times some negatives, which would be positive unexpectedly. So that's the reason we require the a sub n's to all be positive. Okay. The series converges provided the following two conditions are met. That a sub n plus 1 is always less than or equal to a sub n for all n's. A sub n plus 1, that means the bigger a sub n is smaller than the earlier a sub n. The later a sub n is smaller than the earlier. In other words, what this is saying, the a sub n's are getting smaller. That's what it says. The a sub n's are getting smaller. And condition 2 is the limit of the a sub n's as n goes to infinity is equal to 0. Well, that's a condition for all series to converge, isn't it? A series diverges if that's not true. Okay, so that's certainly a condition that has to be true anytime a series converges. And so this is a really pretty simple test to apply. It's amazing that this simple, the idea, we just have to have the terms getting smaller and smaller. And in fact, the limit of the terms has to go to 0. The terms being the a sub n part, not the negative 1 to a power part. Now, the test can't be used unless both of these conditions are met. And of course, if condition 2 is not met, the series diverges. We call that the nth term test, or the divergence test is what we called it when we first started talking about series. So all this does is tell us whether an alternating series converges. But it's easy to use. Oh, let's look at an example. Determine if the alternating series test applies, and can we determine using that test whether the series converges. A little extra dot right there, that's n plus 1. That's not a factorial or an exclamation mark. Now, to determine, first thing we have to do is decide what the a sub n's are, because everything depends on the a sub n's. Well, the a sub n's are the piece that doesn't involve the negative 1 to the power. So a sub n is 1 over n. That's the very first thing that we need to recognize. And then we need to decide, are all the a sub n's greater than 0? Of course, 1 over n is greater than 0 for all n values. Okay, so that's taken care of. Now, this sometimes is the harder part of the test. But remember, we had to have a sub n plus 1 being smaller than a sub n. And we have to make sure that that's the case. And that if we're going to have trouble, this is probably where we'll have trouble. But in this case, since a sub n plus 1 is 1 over n plus 1, and a sub n is 1 over n, the denominator here is larger than the denominator here. And since the numerator is constant, the same value, then this fraction has to be smaller than this fraction. So condition 1 of the alternating series applies. That is, the a sub n plus 1 is less than or equal to a sub n for all n's. They're getting smaller. Now let's look at the second condition, and the second condition is this required is the limit of the a sub n's has to be 0. Well, in this case, that's the limit of, that's, this question mark, we have to determine that. Well, in this case, a sub n is 1 over n, so it's the limit of 1 over n as n approaches infinity, and we know in fact that's 0. So I should have a check mark here. The second condition also applies, is true. So we can conclude then that this series converges. Now this by itself is interesting. I don't know if this has occurred to you. This series converges 1 minus 1/2 plus 1/3 minus 1/4. But remember, the harmonic series, which is a p series where p is equal to 1, the harmonic series, which doesn't have the alternating sign pattern, diverges. With the alternating sign pattern, it converges. Without it, it diverges. So here's the harmonic series, which diverges, but the alternating series version of that converges. That's an interesting point. At least I think so. The next problem will, the next example will give us a little more trouble. At first sight, it doesn't look like it will, but here we have, again, an alternating series. It's clearly an alternating series, and we can see that the a sub n is this fraction 2n plus 1 over 3n minus 1, and of course all of these are positive because the smallest n will be is 1, and that would be 3 minus 1 in the denominator, which is positive. Anytime we see subtraction signs, we have to pause and think, will this always be positive? But it will, because everything, because of the nature of our denominator here, its smallest value is actually 2. Okay, so what we have to do to apply the alternating series test is to make sure the terms a sub n plus 1 is always smaller than a sub n. That is, the terms are getting smaller. And so that's where we start. Oh, I already mentioned that a sub n is greater than zero, the a sub n's are greater than 0. But now is this tough question, are the a sub n plus 1s less than or equal to a sub n's? And, imagine if we put n plus 1 into here to find out a sub n plus 1, we'd have 2 times n plus 1 plus a 1 over 3 times n plus 1 minus a 1. So I don't know what that would be, but it would be a mess. I mean, we could write it out, it'd be a mess, and we wouldn't be able to tell whether a sub n plus 1 is smaller than a sub n. We wouldn't be able to tell that. So this is a tool that we've seen before. Why don't we consider the function f of x equal to x plus 1 over 3x minus 1? And from its derivative, we can see whether that function is decreasing. And if that function is decreasing, then that means these have to be getting smaller as well, okay, these a sub n's. And so that's what I've done. I've calculated the derivative of f here, and when I did, I got negative 6 over 3x minus 1 squared. Well, no matter what x is, this denominator we're going to calculate will square, so the denominator is always positive and the numerator is always negative, and so this function is always decreasing. No matter what x is, or no matter what n is, we're getting smaller since this function's decreasing. And so yes, we can conclude that the a sub n plus 1 is in fact less than or equal to a sub n for all n's. But when we go to check out condition 2, okay, the limit of the a sub n's is actually 2/3. We can calculate that real easily, can't we? It's actually 2/3. So we can't use the alternating series test. In fact, we might say no conclusion. And actually, I guess I misstated myself previously. I'm thinking here, just a moment. Well, strictly from the alternating series test, we have no conclusion because the limit of the a sub n's is not equal to 0. It has to be equal to 0, so we have no conclusion. But maybe we ought to consider the divergence test. Which test could we use? And I would say that we could use the divergence test and find out here. This is a big mess, okay? Here's where I'm at, okay? Way back up here, I kind of paused a little too early here. Now, to use the divergence test, we actually wouldn't be just looking at the a sub n's. We'd have to be looking at the entire piece to use the divergence test. But if the limit of this part of the entire term isn't equal to 0, then the limit of this part together can't be 0. So because condition 2 fails, actually, I shouldn't say no conclusion. Because condition 2 fails, then this is actually a divergent series. Okay, that's what's strange about the alternating series. We just have two conditions. If they're both met, then it converges. If the second one is not met, then it diverges. So we had the issue in this one first was decide whether the terms were decreasing, before we went on. Maybe we would have been better off by looking at the limit of a sub n's first, and we wouldn't have gone through the other trouble. Okay, well, let's look at this next example, and like I said, maybe it's worthwhile deciding in advance whether the limit of the a sub n's goes to 0 or not. Maybe that's the better thing to do in some cases. I don't think so in this case. Here we have an alternating series again, and the a sub n's, of course, are the square root of n over n plus 1, which those are always going to be positive. And so we've got that met. That's the first condition that has to be met. Now the next question, can we tell whether the a sub n's are actually decreasing? That is a sub n plus 1 always less than or equal to a sub n? And when we look here, here's the a sub n plus 1. All we're doing is increasing, well, we have an n plus 1 in this position under the square root, and we have an n plus 1 in this position in the fraction, and then plus 1 gives us the n plus 2. So what we're doing is we're comparing this fraction to this fraction, okay? We want to know if the a sub n plus 1 is smaller than the a sub n. The problem here is, of course, the denominator is bigger here, but so is the numerator. And if you're changing both the denominator and the numerator, and they're both bigger, then we don't really know how it compares to this other fraction. So we're kind of stuck with doing the same thing we did in the last example. Let's consider the function f of x equals square root of x over x plus 1, and let's determine whether it converges, or whether it's decreasing or increasing or what. And the way we do that, we know a function is decreasing whenever its derivative is negative. That's what we know. So I've taken, and it took a little work, I've taken the derivative of this function, and I got the fraction x minus 1, this is hard to read, divided by 2 times the square root of x times x plus 1 squared. Now, for all x's that are 1 or bigger, and that's really all we care about, right? Because we're comparing to n's that are 1, 2, 3, 4, and so on. So we only care about the x's that are greater than or equal to 1. And in the denominator, if x's are greater than or equal to 1, the denominator is always positive. In the numerator, when x is 1, we have a 0, but when x is bigger than 1, then we have a positive number. And so this derivative is no bigger than 0. It's only 0 when x is 1, and when x is greater than 1, then it's negative. Ooh. Absolutely not. It's positive, isn't it? Well, let's see what my issue is here. Okay. Let me pause on this. Well, for some reason I miswrote the derivative of f, and so I apologize here. We should be scratching this part out. The derivative of f is 1 minus 2x over 2 times the square root of x times x plus 1 squared. Now, when x is 1, in fact, when x is 1 or bigger, the numerator is going to be 1 minus 2 or 1 minus something bigger than 2. So it's always going to be negative. My bad over here. And the denominator is always going to be positive for these x's. So this fraction, since the numerator is negative and the denominator is positive, for x is greater than or equal to 1, then the fraction itself is negative, so the derivative is negative. And if the derivative is negative for x is greater than 1, that means the function f is decreasing for x is greater than or equal to 1. And so that tells us that a sub n plus 1 is always less than or equal to a sub n's, because the a sub n's are decreasing. That's the whole point of what we went through here, the reason we went through all that trouble. Now, what about the limit of the a sub n's? Is that equal to 0? And of course, the a sub n is square root of n over n plus 1. And so when we calculate this limit, what we'll do is we'll multiply numerator and denominator by 1 over n. And when we simplify the square root of n over n, we get 1 over the square root of n. And of course, we get 1 over 1 plus n in the bottom when we multiply by 1 over n in the denominator. And so in this case, the limit of the numerator is 0 and the limit of the denominator is 1. and let me remind you, you can always slow this down. You can pause and think about some of these steps as we go through them. But I don't want to belabor the point. I know that you're an expert at finding limits at this point. So the limit of the a sub n's is 0. The a sub n's are decreasing, and so by the alternating series test, the series that we were looking at and determining, yes, in fact, does converge. Okay, let's look at the next example. Consider the series sum from n equal 1 to infinity of n over negative 2 to the power n minus 1. Now here we don't see the negative 1 to a power, but we do see a negative number to a power. And so it's not really clear immediately whether this is an alternating series or not. But this makes me think, because I have a negative number to a power, that it may be. So let's stop and look at what we've got going on here. Negative 2 to the power, this denominator, negative 2 to the power n minus 1, well, negative 2 could be thought of as negative 1 times 2, and that's what we have to the power n minus 1. And then we could apply that power n minus 1 to the factor negative 1 and to the factor 2, and then that basically gives us an alternating series scenario. It happens to be the power on negative 1 is an n minus 1. Now remember, this is down in the denominator, but it's just going to be a 1 or a negative 1, isn't it? See, this is really part of the denominator, but the fact that it's just going to be 1 or negative 1 is just changing the denominator, so we can think of it out here separately. Okay, so here we have the exponent on negative 1 that is a little different, but it's still going to alternate. When n is 1, this exponent is 0, so we have a 1, positive. When n is 2, this exponent is 1, so we have negative 1 to the first power, or a minus. And you see that it's going to alternate in that fashion. So it really is an alternating series, although it's disguised from us a bit. So, and now when we look at it, see, we've got to do this to decide what the a sub n's are. The a sub n's are this portion. See, we couldn't look up here at the original series and tell that. But now we know the a sub n's are this portion right here. And knowing it's this portion, then we can decide, oh yes, those a sub n's are always positive. And that's a pretty critical issue here. We couldn't look here again. We have to look here to decide what the a sub n's are. Okay. Now, next question is, are the a sub n's getting smaller? And what I've done here, once in a while I kind of think this way. What I've done is I've checked out a sub 1. I put in 1 in. See, a sub 1 is 1 over 2 to the 1 minus 1, which is 1. A sub 2 is 2 over the 2 to the power 2 minus 1, which is 1. A sub 3, okay, a sub 3 is 3 over 2 to the power 3 minus 1. That's 3 over 4. And I calculated a sub 1, 2, 3, 4, 5, 6, and maybe beginning to see a pattern of what's going to happen. I'm betting that if I look at a sub 7, I'm going to get 7 over 64. So these, I'm going to say, because I see this pattern, are clearly getting smaller. The a sub n's are clearly getting smaller. But we understand that this is not always adequate. We've looked at several examples where we might not be able to tell that. But here it's pretty clear, when they're not really a question, these are in fact getting smaller. Okay, just because of the pattern. Now, we could be a little more precise here, maybe. Let's look at this. A sub n plus 1 is n plus 1 over 2 to the n. And maybe we could tell, look at this, maybe we could tell that 2 times n is always going to be bigger than n plus 1. Isn't that pretty clear? 2 times n is always going to be bigger than n plus 1. mean, n plus 1 is smallest when n is 1, isn't it? And when n is 1, this is 2. When n is 1, this is 2. As soon as n goes to 3, this is going to be twice that. This is just one more. And so n plus 1 is always smaller than 2n, or equal to, for n's that are 1 and larger. The denominators are the same, so this fraction has to be bigger. Now this fraction will actually simplify. Okay, this fraction will always simplify. This fraction will simplify by simply thinking of, notice, what we can do with this fraction is we can think of 2 times n and 2 times 2 to the power. In other words, I'm multiplying, I'm not explaining this well here. The fraction right here. Okay, we can think of it in this fashion, is it's 2 over 2 times n over 2 to the n minus 1, because when we multiply the 2 and the 2 to the n minus 1, we add the exponents, so our exponent is n. Here we just have a 2 times n. So this fraction can be written as 2 over 2 times n over 2 to the power n minus 1, and since 2 over 2 is 1, then these two fractions are equal. That's all I was saying. It took a long time to say that, but that's what I was saying. I'm just going through this idea that we can always prove that this is true, and that's what I've done here. I used an argument to try to convince you that n plus 1 is always less than or equal to 2n, but here's what we could do. N plus 1 minus 2n is 1 minus n, and 1 minus n for n's 1 and bigger is always going to be less than or equal to 0. So that means if I add 2n to both sides here, n plus 1 has to be less than or equal to 2n. It's a little different argument, and it's hard to do talking and not writing and pointing so much. Okay, so first we kind of decided that we thought that they were getting smaller, and then I went through a little formality, and I didn't clear this up, because this is a sub n right here, isn't it? See, this is a sub n. Here's a sub n plus 1, and going through the arguments below here, I've proven, if you will, that a sub n plus 1 is in fact less than a sub n, less than or equal to a sub n. So they are in fact getting smaller. So the next thing to do is consider the limit of the a sub n's, and that would be this limit. Now, as n goes to infinity, which I got lazy and didn't write, we have an indeterminate form of infinity over infinity. When n goes to infinity, the numerator is going to infinity, and so is the denominator. So L'Hopital's rule will apply, and when we use L'Hopital's rule, we take the limit of the derivative of the numerator over the derivative of the denominator. Well, the derivative of n with respect to n is 1. The derivative of 2 to the power n minus 1, we have to go way back. It's the natural log of the base 2 times the derivative of natural log of the base 2 times 2 to the power n minus 1 times the derivative of the power n minus 1, which is just 1. So this is what the limit looks like, and I'm just reminding you. And that limit is in fact 0, because the denominator, this is constant, but this is getting unboundedly large as n goes to infinity, isn't it? So that limit is in fact 0. Well, then that means both conditions of the alternating series test apply, which means the alternating series that we just talked about, that we're dealing with, in fact does converge. So a long way around that. This one's quite involved, and you may want to go back and look at this again. In some cases, I kind of rambled through it. Well, this is the last series we're going to look at using alternating series test, and it's the series, and clearly you can see it's an alternating series. These terms are all positive. And so we would start considering, and these are the A sub n's, aren't they? We'd start considering the test. Now, of course, first test is to see whether the A sub n's are decreasing. And then the next part of the test is to look at the limit of the A sub n's as n goes to infinity. See if that's zero. And I think on this test that I looked at that in the order, but I'm concerned right away when I look at this A sub n, those don't look like they're going to zero. See, I mean, this is always bigger than this, and so we're expecting, and the numerator's always bigger than the denominator, and so how can that be getting close to zero? And so we really could have foregone all of the things that I did above here. The real issue is the limit of the A sub n's, and the limit of n plus 1 over n, which is A sub n, is in fact equal to 1. It's not 0. And so the alternating series test does not apply because condition 2 fails. I didn't even need to look at condition 1. Now, that really tells us that the series diverges in this case, because if we looked at the limit of this whole term, including the negative 1 to the power n plus 1, this part's getting close to 1. And so what's happening is these are getting closer. In some cases, we're getting close to 1. Some cases, we're getting close to negative 1 as this changes. And so that, in fact, means the limit of the negative 1 to the power n plus 1 times n plus 1 over n. If we looked at that whole limit, if we looked at the limit of the terms of the sequence of the series, they can't go to 0 either. And so, in fact, we know this series, in fact, diverges. Alternating series test doesn't apply, but because the second condition failed, then we know, in fact, the series diverges. That's kind of a plus side of this test, I guess, under those circumstances. Well, there's more to this chapter that we're in. There's two other things that we talk about when we talk about alternating series test. We talk about approximating the value of a convergent alternating series. There's a test for approximating the value. Early on we had approximating the value of a series of positive terms. Now we can actually approximate the value of a convergent alternating series, and here the terms aren't positive; they alternate between positive and negative. And the other thing that we'll do, that will be a separate lecture as well, is talking about absolutely convergent and conditionally convergent series. Those conditions, which we briefly mentioned absolutely convergent previously when we talked about the ratio test and the root test. But for the alternating series test per se, this is the end of that lecture, and we'll have a couple of other lectures to deal with the other issues. Okay, signing off.